Okay, so we looked at 3D inductors last time. They're called 3D inductors because you use multiple layers. And so some last few points before we close out inductors completely. So the reason we are so paranoid about the Q of inductors is because when you create LC tanks, more often than not, the Q of the overall LC tank will be dominated by the Q of the inductor. Okay, so that's the reason why. Depends on the inductance Q. Okay. And so to increase Q, there are some more, I guess, some care you should take when designing inductors. Some of these are, so don't place any substrate contacts near the inductor. Okay, substrate contacts tend to degrade the Q by quite a lot. And of course, in other words, actually you shouldn't place anything at all close to an inductor. Okay, substrate contacts makes the Q worse, but if you place, for example, circuits or let's say other metal lines close to it, you will degrade the capacitance, so which means the self-resonant frequency. So you try not to keep anything close. So you try to normally give some extra guard space around the inductor. Okay, the other thing you can do is add a guard ring. So a guard ring is a bunch of you can strap it up. So it's a bunch of substrate contacts which are placed far away from the inductor, and it's strapped up with metal lines, with a bunch of metal lines. So it kind of shields the inductor from anything outside. Okay, so you both electromagnetically as well as through the substrate. The other advantage of doing this, you provide a good boundary condition. That is, the inductor. So as long as you don't place anything inside the guard ring, you provide good boundary conditions for the electromagnetic operation of the inductor itself. Okay, and of course no metal fill. Everybody knows what metal fill is. So when you at the end, just before sending the circuit for layout for fabrication, you will do what is called metal fill. So there is a certain minimum percentage of density of metal required for process integrity, right? So for example, you might have minimum density of, let's say, M1 or M2 to be 50% or 70% or 80%. Okay, so what that means is, if the density in a particular area is less than that, less than the prescribed value, you could have some process level effects which could degrade your circuit. Okay, so the foundry tells you, like, mandates that you have a minimum amount of density. However, you don't want to put any metals close to your inductor, right? So what you do is you try to get an exception from the foundry. So you let the foundry know that you are adding an inductor, so they'll give you some directions. You know, you might add some extra metal fill around the guard ring to help with density, but you might get an exception just around the inductor itself. Okay, and I guess you need to maintain symmetry, because you can yes.
Don't place the second point. Why the substrate contact shouldn't be near the inductor? You're saying guard ring should be placed.
So the guard ring should be placed far away. Okay. So for example, let's say you have this inductor, right? So if you want to, let's say you have a certain inductor like this. Okay. So what you would do is, don't place any substrate contacts in this region.
Shielding also, secondary substrate contacts is actually a technique that does not flow.
How would you put substrate contacts? See, substrate contacts basically give a path from M1 to the lowest metal to the substrate. You don't want to add those kind of low impedance paths in the electromagnetic field of the inductor itself. Okay, so if you have a shield, okay, let's say you have an M1 shield, you don't want to actually connect it to the substrate. The whole idea of adding it is to shield the substrate from the inductor, right? Or rather, shield the inductor from the substrate. Okay, so what you would do is, no substrate contacts nearby, but you might end up putting, let's say, let me use a different color. Okay, so you might end up using, let's say, actually, let me add a circular shield, because this happens to be a circular inductor. but you might add a guard ring like this, which is maybe, let's say, 50 microns away, which is quite far, right? So let's say this was 200 microns. So let's say the diameter was 200 microns, you're giving another extra 50 microns, which is actually quite significant. Okay, so that makes sure that, so the whole idea of giving this, nothing comes close to the inductor. Okay, all your circuits will be somewhere outside here. The only thing you will allow to go outside are the, let's say, the contacts of the inductor itself going outside, and that's the only thing you will allow to go outside. Okay, the guard ring should be connected to a good ground. Okay, so you would connect the guard ring, so you would have bunch of contacts, and then you could strap it up with very good metal. Okay, so maybe all the way up to metal 5, so that you get a good grounding all the way across. Then what you would do is, this would be connected, this would be routed to a pad. So let us say this is your ground pad. Okay, so this would be routed to your ground pad to give the closest and cleanest ground pad, so that you get a good connection. The other advantage is, of course, you also want to prevent any noise. For example, if you have any substrate noise, right? If you have a noisy circuit here which is injecting noise into the substrate, the idea is this substrate contact, this guard ring will pull up all that noise and divert it to a low impedance path, which is ground. That is the idea. Okay. Now, coming back to our points, symmetry. Okay, you can show that if you excite an inductor symmetrically as opposed to single-ended, it actually has a slightly better Q. Okay, you can show that. So you try to maintain symmetry. And be careful about VR resistance, because let's say, remember, to actually take this out from, take the inner node outside, you have to go to a different metal. Okay, so when you go to a different metal, you will have to use vias. Vias are connecting layers between different metal layers. Okay, and those vias usually have very high resistance per via. So what you need to do is use a bunch of vias, maybe all the way, if your inductor trace is, let's say, 5 microns across, try to use the whole width, cover it with inductors, and maybe a big square, so that, let's say, if your via of each, let's say the resistance of each via is, let's say, it could be 5 ohms, okay, 5 or 6 ohms, whereas the resistance of your metal trace would be in milliohms, tens of milliohms. Okay, so what you would do is, if it's, let's say, it's 5 ohms, you would use 100 of them in parallel to bring the resistance down to 5 milliohms, or 1000 of them in parallel to bring it down to 5 milliohms. Okay, so try to use as many vias as possible when you are trying to move from one metal layer to the other. Okay, I think that's it for as far as inductors are concerned. So we'll move on to capacitors. Okay, so what you'll see is, if you have some specialized processes, right, RF processes, you might have some special insulator layers, so what are called high K dielectric layers. So obviously that adds cost, and because it adds an extra process step, and the material itself may be expensive depending on what material you choose, but basic idea is, if you have a special RF process, you might have what is called a MIM capacitor, or a metal insulator metal capacitor. So you have a special insulating layer between two metal layers, okay, which is very dense. So you try to use a high K dielectric, okay, so to get more capacitance density. Okay, how about standard processes? So this would be a specialized process, so you may not have access to that, right? So how about a standard process? So there are one or two options. So the main idea is, you know that in between your metal layers, what do you have? What is there in between metal layers in a semiconductor? You have oxide, right? So what you can try to use that oxide to create capacitors, what are called MOM capacitors, right? Metal oxide metal capacitors. Okay, the problem is quite often you would find you want to actually intentionally, normally in a process, you want to actually reduce the capacitance between different metal layers, because when you route, right, you don't want, if one line is routing over the other, you don't want extra capacitance. So normally you try to make that oxide layer thick. So what that means for us is, typically these kind of MOM capacitors have very low density. Okay, for a given area you will get a very little amount of capacitance. Okay, so the other okay, so let's look at this. What is the capacitance? So let's say you have two metal layers. Okay, so let's say we have two metal layers, right? So let's say the width is W and the length is L, and let's say the distance between the metal layers is D. Of course you know this very well, I just wanted to add it in there, right? Epsilon times by D, right? Epsilon A by D is very well known. Okay, and this obviously this thing is epsilon naught epsilon R, right? And the relative permittivity for oxide is somewhere around 4. You'll see slight variation 3.9 to 4.1, but 4 is a good a good number to use. Okay. What is the typical capacitance per unit area? You'll get somewhere from 0.1 to 0.2 femtofarad per micron squared if you try to use some between two metal layers. Okay, it's very not very dense at all. Okay, now another obvious problem is, if you look at this bottom plate, it is closer to the substrate, right? So you have what is called bottom plate capacitance, right? So this is your substrate. Sorry. So obviously this is substrate is grounded, but you have extra capacitance to ground. So let's say you're trying to use a capacitance like this, right? To use it as an AC coupling cap. What you actually have is, you actually have some capacitance to ground, some parasitic capacitance to ground, and this parasitic capacitance can be quite high, like 30-40% of your this main capacitance. Okay, so what you can do to help with this is, instead of using a vertical capacitor, you try to use the, so what do you know, if you take CMOS processes in general, as your dimensions get scaled, you know that metal layers can be placed closer and closer to each other, sideways. So what you try to do is use the sideways capacitance so because now even though the metal layer may be half a micron thick, the spacing between on a particular metal layer, the spacing between two lines can be much lower, 0.1, 0.15 or 0.2 microns. So you can actually get higher capacitance. Okay, so you can try to think of, let's say, I'll just draw a simple comb structure here. Okay, you can think of a structure like this. So these are your two plates. You actually have sideways capacitance, right? Lateral capacitance between these two layers. Okay, and these are a little bit more dense than this guy. And the other advantage of this, once you do this, you can actually, depending on how much substrate capacitance you can tolerate, you can actually do this on multiple metal layers and connect them up in parallel. Okay, so you can try to increase the density that way. Okay, so now two other things you should know: fringe capacitance. Okay, so if you go back to your original case, right? So you expect all your field lines to go like this, right, between the two plates. But in reality, what happens? You actually have field lines which go outside actually, right? That's basically a fringing cap. Now in this case, what you're actually doing is you're depending on the fringing cap to provide you capacitance. That's what you're doing, because really fringing cap is your sideways cap, right? Electric field lines coming out from the side. So you're trying to use that to create a capacitance. Okay, so you should just be careful. So if you're doing this kind of capacitance, be careful about the fringe capacitance. Okay. Now, how about the temperature coefficient? What do you think? Probably not very high, right? You're using two metal lines, and really the only thing which will change the capacitance is here. The distance and W and L will change by a little bit, but not significantly, not significant enough to change your capacitance by too much. So Temco is quite small. Okay. What else do you know? So this, we looked at the comb structure, right? So the comb structure looks pretty good. Actually, it looks good, but there are actually other ways where you can increase the density even further. So have any of you heard of fractals? So what is a fractal? The idea is you start off with, okay, so the idea is at different, I guess at different levels of resolution, things look the same, right? That is what a fractal normally looks like. So what you can do is, what you're trying to do here is, you want to increase the perimeter as a function of your total area, because it's your perimeter which gives you sideways capacitance, right? For a given area, if you try to maximize that, you'll increase the ratio of your actual capacitance to your parasitic capacitance to the substrate, right? And so happens that fractals can actually give you very good, fractals can give you very high perimeter to area ratio. Okay, so what you would do is you would start off with a very basic template line and connect it up such that you come up with larger and larger structures. Actually, there is a nice paper in 1998 published from Stanford, where they actually explored this idea and they have got very good results. Okay. So you're trying to increase the perimeter to area, right? Okay. So now, what other kinds of capacitance do you know? I assume you all know by now that the MOSFET has an input capacitance, right? Has actually a bunch of capacitors, but yes. So actually there are many kinds of fractals. Okay, depending on which kind of fractal you use, you can actually get different areas. So the idea is I don't know if I remember enough of the structure to draw it here, but let's try. So you might start off with a basic template which looks like this, right? Something like this, right? And you try to connect it up. So what happens? So for example, you can try to get something like this. So if you just reverse this, right? So you can actually get something like this. Okay? And you can keep adding it here depending on which way you rotate it and add it. So you can keep increasing the size in the X and Y dimensions, right? So finally what you'll get is, and of course you also need to have the other side of the other plate of the capacitor. The final idea is you want to increase your given perimeter. So the number of, for example, it will depend on the template you choose. And unfortunately I can't, I'm not able to remember the exact structure which people used in that particular work. But the idea is actually very simple. Okay. So the idea is to keep replicating that basic template and create larger and larger structures. You keep zooming in. Okay. So what happens is, let's say you take this kind of structure, right? When you look at it from a macro point of view, you will see the same kind of structure. When you zoom in, the edges keep looking the same. Okay. So the MOS capacitor, right? Okay. So next class we'll look at the different kinds of capacitances of a MOSFET. But what is the highest? Which node of the MOSFET has the highest capacitance? The gate. Right, the gate capacitance is the densest, so you probably want to try to use that, right? Okay. So you want to use the gate capacitance CG. Okay. Now it so turns out so that this has actually pretty good density. So if you look at the MOSFET, right? Yes.
NMOS today is NMOS because we can never operate NMOS activation. Activation of the chip.
Actually, yes. So we'll come to that. Okay. So we are actually going to look at that next. Okay. Whether we want to use NMOS or PMOS, and whether NMOS actually has some other advantages, and the process itself might have some ability to give you an NMOS capacitor which never enters accumulation. Okay. Or so you might have that option by changing the, actually you don't have to change the process, you don't have to add an extra process step, but we'll see that you need to change the process procedure slightly. Okay, so we'll take a look at that. But assume for now that we are using an NMOS. I mean, of course, you can also, as he has suggested, you can also use a PMOS, right? And of course, I mean, really the TOX between an NMOS and PMOS is not that different. So for a given width and length, your capacitance will be almost the same. Okay, and the kind of densities it gives you. So it gives you approximately 1 to 2 femtofarads per micron of width, and assumes, and this of course assumes minimum length. Okay. So let's say your minimum length in your process, in this course we are using a 130 nanometer process. So let's say your minimum length is 0.13 microns. So if you take a device which is, let's say, 1 micron over 0.13 microns, the capacitance may be like somewhere between 1 and 2 femtofarads. Okay. And if you take a 2 micron by 0.13 micron, you might end up with something maybe 2 to 4 femtofarads and so on, right? Depending, it will just be a multiple of your basic, it will depend on your width. Okay. Now going back to your TempCo. Okay. This could have a larger temperature coefficient. Okay. And more importantly, as we'll see soon, it actually, the behavior of the capacitor itself will change with temperature. Okay, because it depends on certain fundamental device parameters. Okay. Now how would you use this? Obviously you have a gate capacitance, right? So that's one end of your capacitor. What about the other end? So we'll try to do something like this maybe, right? You want to maximize the capacitance, right? So the other end can be connected to ground or VDD or the appropriate voltage. Okay. So next we'll see what happens when you connect your bulk. Okay. So let's call this bulk. So we are actually looking at C gate to bulk. So we are going to strap all the other 3 terminals together and look at the capacitance. Okay. But what this means is your bulk voltage actually, or even your drain source, right? So those nodes cannot be connected indiscriminately to any voltage, right? So what it actually gives you is very good single-ended caps. Yes. That's what we are, okay, that's the next point. Okay. So what you will see is, you can use them only in cases where the signal levels are very small. The reason is the capacitance is a function of your voltage that you apply to the capacitance. Okay. And so why would you use it? You'd use it in cases, for example, so actually let's just move on to the next page. So you'd use it in cases like, oh man, okay, I wish this had screws to tighten it. Okay, so where can you use it? So you can use it for, let's say, single-ended filters, right? Where the signal levels are small. So let's say you need you need this kind of RC filter, right? You can use it in such a case where the signal levels are small. Where else can you use it? So let's say you have a block. Have you heard of supply bypassing? No. Okay. Some of you have heard about it, some of you have not, right? So if you take any random circuit, right? Now, if you look at small signal analog circuits, they tend to draw a constant DC bias current from your supply. Okay? But more often than not, in RF circuits, you will see much larger signal levels and several kinds of switching circuits. Okay, what that means is the current you are drawing is actually not just a constant value, but it might be switching like this, or you might have sinusoids, you might have all kinds of harmonics. Okay, and now remember that this is in your simulation, you'll start off with using an ideal source, right, ideal VDD, but in reality you have some give me a minute. So in reality, what you have is some parasitic inductance, right? Remember, you have to go off chip to actually connect your supplies. So you could have a very large inductance. What happens when you try to draw a switching current through an inductor? What kind of voltages will be? V is LdI by dt, right, for an inductance. So if you actually look at the voltage here, it's going to have a very crazy kind of profile. So you could have lots of dips and peaks in the voltage profile here. Okay. So to help with that, so let me actually, so to help with that, what you're going to do is add a capacitance here. Okay. Yeah, so you're going to add a capacitance here. Okay, so what does that capacitance do? The capacitance tries to, remember that the inductance tries to, right, it tries to give a stable current through it, and otherwise the voltage tends to change. The capacitance tends to keep a constant voltage. So what happens is, the circuit, the stable current is drawn through this path and the switching current is drawn through this path. Okay, so the capacitance acts as a reservoir of charge. Okay, so that's the idea. So in these kind of cases, remember that now once you add your capacitance, this is constant at VDD, right? The ripples in your supply are reduced a lot. So what that means is you can use MOS capacitors. You actually want very dense capacitors in this case. Okay. Have you guys heard of a device called a Varactor? Some of you have, I think, but others may not have. So Varactor is simply a voltage controlled capacitor. Okay. Okay. Why do we want to use a Varactor? Where would you use a Varactor? So let's say you have a resonant circuit, right? You have an LC. Okay. Suppose this capacitance could be changed. Remember that, right? Your frequency of, so if you change the capacitance, your frequency can be changed. So these kind of devices are used in voltage controlled oscillators. Okay. So circuits where you want oscillators, but you also want to be able to tune the frequency of the oscillator. So you would use these kind of devices. Okay, so let's see, can any of you think of some devices whose capacitance varies with voltage? Diode is a good example. Why? Because if you take a reverse bias diode, it has a depletion region, right? And the depletion region width changes with your applied voltage, right? So that is one kind. So let's look at that first. So let's call this VR. So this is how it varies. So this is the equation. So depending on how your junction is doped, right, this M could change. Okay, if you take an abrupt junction, means the doping level changes suddenly, right? So I think you might remember the abrupt junction case from your devices class, right? I'm sure you remember that. And if you take a typical CMOS process, so obviously an abrupt junction would give you 0.5, but CMOS process will typically tend to have almost abrupt. So you might have an M close to maybe 0.3 or 0.4, somewhere around there. Okay. Okay. I'm doing a really bad job of this writing. Okay. So you could have maybe somewhere 0.3 to 0.4. Okay. So then, what is so special about? So this is the symbol for a Varactor diode, right? Because you know you're specifically designing it for a capacitance variation, right? So what is so special about this? So remember that we wanted to use it for tuning the LC tank, right? So let's say you want to maximize your tuning range, maximize the range of frequencies over which you want to tune the tank. What that means is you want to maximize Cmax over Cmin, okay? So you want to maximize Cmax over Cmin. So you would change the doping profile such that you maximize Cmax over Cmin. Then you may want a specific way of varying your capacitance with voltage, right? So you might be able to change your doping profile such that you get a specific, maybe linear or quadratic or something like that. Okay? So you might want to do that. That may be something, you know, more exotic, but you might be able to do that. Okay? So now so this Varactor, you would find it in a specialized RF process, but not so common in a standard CMOS process. Okay? So now let's look at your MOS Varactors. Okay, so controlling voltage is of course this, right? So it's not a 3-terminal device. All of these voltage control capacitors, as it turns out, are not 3-terminal devices. They're actually 2-terminal devices. Okay, one terminal is biased at a particular voltage. The other terminal voltage of the other terminal actually sets the frequency. So sets the capacitance. Yes. Yes. Yes, that is right. So typically what will happen is, since you have a signal around it, you won't get the exact same curve as you did with a DC, right? You would get a steady state curve, Cmax, not Cmax, capacitance versus voltage curve. And if you apply a small signal around that, it would follow the same curve. But in reality, when you have a very large signal, right, what will happen is it will go through multiple regions of that C to V curve. So you will get an average capacitance to voltage relationship, right? So you will have to live with that. So in cases, yes, so in cases where the signal is small, you can afford to do that. You can afford to bias it properly and do that. Okay? In cases where the signal is inherently large, you don't have any choice, unfortunately. Okay? Yes. So the thing is, but even the MOS Varactor is actually a 2-terminal device. It's not a 3-terminal device, right? So if you have a PMOS, so what you would want to do is you would end up connecting your NVL to your maximum, to VDD, right? To get the inversion mode device, right? So if you do that, then you have only the gate and then your source drain. But if you don't connect it to VDD, you have to be very careful, because if the signal levels cross a lot of VDD, you might go into non-monotonic regions. We'll look at that, right? Okay. So what we're going to do is take a MOSFET. Let's, in this case, okay, since we'll take a PMOS. Okay. We're going to, let's first start off with connecting all three together, see what happens, then we go on, see what happens when you try to disconnect some terminals, right? Okay. So what do you think is going to happen? You must remember this from your devices, right? So let me call this capacitance versus voltage. So let's say we sweep it from, I don't know, some very negative voltage to very positive voltage. What is the capacitance going to do? Okay, so let's start off from one direction, right? Let's see. Okay, so we're going to, this is your bulk to gate voltage, right? Bulk to gate voltage is positive for a PMOS. So let's start off there. So what happens when bulk to gate voltage is very large? So typically this is the NL of your PMOS, right? Normally during normal transfer operation it's connected to VDD. So you know that VBG is going to be positive. So let's start off from there. Okay, what is going to happen? So when VBG is very large, what region do you think the transistor is going to be in? Okay, so saturation normally, but in this case your VDS is 0, right? So you're going to have some capacitance, but if you look at your device, so let me draw the so it is going to be in linear region for sure, okay, but let's look at the cross section of the device. So let me call this the source, the drain, the gate, and this is your N-well, right, which is your, in this case, the bulk. Okay, so what is going to happen? What is going to happen when VBG is very large? Is there going to be a channel? First of all, there's going to be a channel, okay, but, and you know it's linear region, so it's going to be a channel all the way from source to drain. Okay, so you are going to have a channel, so it's going to be a straight channel, right? Okay, that's good. Let's do it this way. Okay, you're going to have a full straight channel. Okay, now what is the capacitance between gate to bulk? Cox. So what is Cox? So it is just, so okay, so let's call this P, okay, so let's call the capacitance of just this, right? We're going to call it Cox. What is this? So let's say this thickness is Tox, okay, so Cox is epsilon, let's say epsilon A by Tox, actually epsilon by Tox, actually Cox is defined as epsilon by Tox, right? It's proportional, it's per unit area, right? Okay, so you're going to have Cox. So this, let's call this Cox. Okay, so what happens if you keep reducing VBG? Right? So this, what is this region called? Inversion, right? Okay, this is strong inversion actually, right? Okay, and what happens at, so, right, you will enter moderate inversion, weak inversion until it goes down, and at that point obviously as the channel vanishes, right, the capacitance keeps reducing. Okay, and then you have accumulation region where you actually have a depletion region, right, where the channel used to be, right, and the depletion region width keeps decreasing, right, so the capacitance keeps increasing until you reach what is called accumulation. Okay, so this is your accumulation region where the voltage VBG is so negative that you have actually created a bunch of charge carriers here, right? So your VBG is so negative that you actually created a not a channel, but a bunch of charge carriers have been attracted to the channel where the channel used to be, and this is your depletion region capacitance. So you basically have 5 regions. Okay, so you have some. So 1 is accumulation, 2 is depletion, 3 is weak inversion, 4 is moderate inversion, and 5 is strong inversion. And at accumulation again, the capacitance is going to be Cox. Okay. Now this is your capacitance to voltage curve. Now one thing to know is in strong inversion, okay, actually we'll come to this later because it's not particularly relevant right now, but the one thing to note is it's non-monotonic. Okay, what does that mean? So if you want to use it in a circuit, right, so normally you want very either like very well behaved functions, right? So if, for example, if you're going to tune it tune the frequency of an oscillator using a voltage, right? You want it to go from one end to the other. You don't want to have multiple values. The reason is you would end up using the oscillator in a closed loop form, using a phase lock loop, right? You don't want it to lock at two different points. Okay. So how do you prevent this? So you have two ways of preventing this. So one is called the inversion mode varactor, where you're going to try to prevent the transistor from going into accumulation. Okay. How do you do that? Okay. You have your drain, source, gate, and you have your bulk, right? What we are going to do is take your bulk and connect it to VDD. Okay, and then now you are going to look at the capacitance between gate and drain source. So what happens now? Now, as far as high VBG is concerned, you're still going to have the same behavior, right? You're going to have Cox. It's going to go through inversion and everything, but you're basically going to prevent it going into depletion and accumulation. So the capacitance will look something like this. Okay, so this is a nice way of making your capacitance non-monotonic. So you have some certain minimum capacitance and your maximum capacitance. So that's well and good, right? Okay. So now one more thing you should know. So let's go back to the yes. Yes. Oh, one more slide. Sorry. Okay. Yes. Yes, you can. Yes, you can. But you just have to be a little bit careful, because I'll tell you why. We are just coming to that. So, what is this voltage here? This is related to the threshold voltage of your device. It's VDD minus VTH, right? For your device. Is that right? The only thing you have to remember is what happens when you disconnect your bulb from your source, right? This side is going to shift. Your VDD minus VT is going to shift, right? So you have to be a little bit careful, because if you decide to play with VDD, you also have to be careful about where you're going to bias your device overall, right? Because you need to bias the two nodes of your capacitor at some point, right? So you have to be a little bit careful about that. But apart from that, you could probably get away with it. You could probably get away with changing your VDD to some extent. Okay. Now, obviously the NMOS cap will also show a similar effect, right? So except that the curve will be shifted. Oh, sorry. Good point. Right? Okay. Obviously, I hope everybody understood the substrate effect, right? You remember that. The fact that if your source and bulk are at different voltages, your threshold voltage of a transistor actually changes. Everybody remembers that, right? Just want to make sure. Okay. Now the other kind is, let's go to the next page, is the accumulation mode varactor. Okay. So how would you do this? So the accumulation mode varactor is made by, you want to prevent the transistor from going into inversion. Now, can you ever prevent a normal transistor from going into inversion when you vary the voltage? You can't, right? So what you would do is, you need to change the process slightly. Okay. So, so remember that you had an N well, right? So Earlier you had P diffusions. Now instead of P diffusions, you create N diffusions. Now this is no longer a transistor. Okay, so it can, because the transistor operation is normally in the inversion region, right? So now this is no longer a transistor, and you prevent this point from inverting. So it is always going to be N type at that point. Okay, so now we can call this VBG and capacitance, right? What happens? So you will have accumulation, no doubt. You would have depletion, but it would never invert, right? Okay. So this is your accumulation MOSFET, right? So let's call this COX, and this is your, we'll call this C depletion. Okay. So some other general things to know is your Cmin, right? Let's look at Cmax over Cmin. Okay. So you know what Cmax is. What is Cmax? Cmax is COX. You already know that. What is Cmin? You're going to have some certain depletion, capacitance, and you're going to, there are going to be other components which are, if you go back to your cross section of your device, if I can find it. Okay, remember that there is some gate to drain and gate to source overlap capacitance. That is also going to limit your Cmin. Okay. Okay, so let's say you want higher Cmax by Cmin. What that means is you want to reduce the proportion of CGD as a function of your overall capacitance. How would you do that? Increase the length of the device, right? So if you want larger Cmax by Cmin, you want to increase the device so that as a function of your overall capacitance, your overlap capacitance becomes a smaller fraction, right? So okay, now this is not an ideal capacitor. You also have some parasitic resistance, alright, associated with this. What is this? You'll have some R channel, right, or R MOS, whatever you want to call it. And what is that? You can show that it is 1 over 12 times, actually it's L over 12 times kPW times okay. Obviously this is an approximation, and it's not going to be valid at VBG equals VT. The resistance never goes to infinite. Okay. This is actually for any kind of device. Actually, obviously for the inversion mode, for the accumulation mode, you don't have this. You don't have a channel, right? But for an inversion mode device, you would have a channel, and this would be the channel resistance. Mm-hmm. Yeah, you are going to have a channel, and it's going to have a resistance, right? Yeah. So you can actually show it's actually not very intuitive. Okay, so obviously the derivation of this is out of the scope of this particular class, but you can show this. Okay, so we'll just take it at face value for now. Okay, but what that means is, so to increase your Q of your varactor, right? What do you want to do? You want lower R MOS, right? So let's call this R MOS. Okay. So you want to reduce your R mass, which means you want to reduce your length. So this is an obvious trade-off. You want a high Q varactor, you'll have to live with low Cmax by Siemens and vice versa. So this is a basic trade-off. Okay, so when you want to design your varactor for, let's say, an oscillator, you will end up having to choose a particular length and width and so on. You'll have to choose it appropriately. Okay. Okay. And finally, I think we already looked at this. The actual characteristics are for DC, right? What we looked at so far. If you have a large signal, you'll have to look at your average Cmax over Siemens, right? Okay, so I think that's it. I think one thing we have to keep in mind is your the way you would connect it, right? So let's say you have this. So let's take the this case, right? So if you look at these two nodes, first of all, the number one thing to remember is there is going to be a difference in the parasitic. You're going to have extra parasitic resistances on this node because the gate node is inherently high Q. Okay, so you have a poly, you have a metal, and you directly connect to it. Okay, if you look at the substrate or the drain source nodes, you actually have a diffusion. You have a bunch of contacts, and then you go through. You get to the metal. So what that means is the Q at this node or the parasitic resistance at this node is going to be lower. So normally you try to connect this to the signal side, okay, and use this as your control node. Okay, that is how you would use it normally. Okay, so we'll stop here for today. Next class we'll look at MOSFET operation. So of course